Hey everyone, welcome to my channel. This is the drone programming with the Python course. Here we are going to learn the basics of a drone, including the components and how the drone flies. Then we will look at the installations and the basic movements along with image capture. From there we will create exciting projects including surveillance drone, face tracking and line following drone. If you are a beginner, don't worry, this course is for you and we will focus on the implementation part so that you can get the most practical experience out of this. And even though we will be using a specific drone for this course, 80% of the material covered in this course can be used with any drone. If you would like to view more of such content, then don't forget to like and subscribe. So let's get started. The term drone means a continuous low humming sound. Now, this might not be the best way to represent these unmanned aerial vehicles, but still it's the most commonly used term. Drones have gained a lot of popularity over the past few years as the technology has advanced and the motors have become cheaper. This has allowed the drones to be used in much more commercial sectors such as photography, filmmaking, surveillance, and even delivery systems. In spite this, drones have a long way ahead. So learning how to program a drone to perform different tasks is becoming an increasingly popular skill. Drones come in different shapes and sizes. A popular term you might have heard for a drone is quadcopter. This refers to a drone with 4 propellers or motors. Similarly, a hexacopter has 6 propellers and an octocopter has 8 propellers. So let's have a look at the main components of a drone. A drone will consist of frame, motors, propellers, electric motor controller, power distribution board, a flight controller, battery, receiver or Bluetooth, a camera, video transmitter, and some sensors. The frame or the body is what holds everything together. Most good drones use carbon fiber as the frame material since it is quite lightweight and strong. Nowadays, a lot of DIY drones use wood and 3D printed frames as well. Motors can be considered as the engine of the system that creates the lift and allows the drone to fly. There are 2 main types of motors used in a drone: brushed and brushless. Brushed motors are simple and cheap, whereas brushless motors are expensive but have a better weight to power ratio. Propellers are what generate the lift force when the motors start rotating. There will be 2 types of propellers for any given drone. One that rotates clockwise and the other that rotates counterclockwise. This is because if all the propellers are rotating in the same direction, the drone will start rotating as well. But since we have half of them rotating in one direction and the other half rotating in the other direction, they can cancel each other out and the drone does not rotate. Propellers can have multiple pairs of blades. The more blades you have, the more thrust it will generate, but the more inefficient they get. The electric motor controller or the ESC is what controls the speed of the motors. They convert the DC signal from the battery to AC signal for the motor. You can have separate ESC for each motor or a single board with multiple ESCs on it. Power distribution boards allow battery to power all the components, including the motors and the flight controller. The flight controller is the brain of the system and it decides what should be the speed of the motors based on the input received from the sensors and the receiver. The battery will power all the components of the drone. This has to be light and efficient at the same time to allow maximum flight time. The receiver or the Bluetooth allows transmission of the signals between the remote and the drone. Most of the times we will also have a camera attached to the drone along with either an SD card storage or antennas for wireless video transmission. Now, to transmit video, we need video transmitter. This device is responsible for the transmission of video through the antenna to your cell phone or the FPV remote. There are multiple sensors attached to a drone. For example, the pressure sensor measures the altitude or the distance between the ground and the drone. The GPS locates the position of the drone, whereas an IMU measures the acceleration and the angles at which the drone is. The movement of a drone seems quite complicated as it has 4 or more motors to enable all movements. But in reality, it's quite simple and intuitive. The drone can move with 4 degrees of freedom, which means it can translate in 3 directions and rotate in 1. As mentioned earlier, 2 propellers of a quadcopter rotate in clockwise direction and the other 2 rotate in the counterclockwise direction. This generates a zero angular momentum that allows the drone to stay stationary rather than rotating in one direction. Let's have a look at the translation movements first. First, we will run all the motors at the same speed that will generate the lift greater than the weight of the drone. This will cause the drone to move up. This is the first translational movement. If we want to go down, we will decrease the speed of all motors so that the lift is less than the weight of the drone. If we want to hover in the air, we will change the speed of the motors so that the lift is equal to the weight of the drone. This will allow the drone to hover above the ground. Now, coming to the second translation, if we want to move left, we will reduce the speed of the left motors and increase the speed of the right motors. To move towards the right, we will decrease the speed of the right motors and increase the speed of the left motors. Similarly, we can translate in the third direction, which is moving forwards and backwards. By decreasing the speed of the front motors and increasing the speed of the back motors, the drone will move forward. For moving backwards, we can decrease the speed of the back motors and increase the speed of the front motors. Since 2 motors are rotating in clockwise and the other 2 are rotating in counterclockwise direction, we can use this knowledge to rotate our drone. To rotate the drone clockwise, we will decrease the speed of the motors moving clockwise and increase the speed of the motors moving counterclockwise. Similarly, if we want to rotate counterclockwise, we will decrease the speed of the counterclockwise motors and increase the speed of the clockwise motors. Now that we understand how the drone flies, let's have a look at the drone we will be using for this course. The drone that we will be using for this course is the Tello Drone. Now, this drone is recommended to be used with this course, but that does not mean that you cannot apply the same techniques to other drones. In fact, 80% of this course is applicable to any drone and only 20% is specific to the Tello Drone. The Tello Drone is produced by the company Rise and it contains DJI and Intel technologies for flight control. It is a compact drone with a camera attached to it that can shoot up to 720p video at 30 frames per second. It is quite easy and safe to use indoors because it has multiple safety features. Now, this video is not sponsored by any of the companies including Rise, DJI or Intel, and this is my honest opinion that Tello is one of the best drones to get started with if you want to learn programming of drones. The best part about this drone is that it is programmable which means using an SDK, we can control the movement of the drone and apply computer vision techniques without any external wiring. That's right, everything will be done over the Wi-Fi and you do not need even a router for it. In fact, they have added 2 antennas which will allow stable video transmission. The total flight time for this drone is about 13 minutes and the flight distance is about 100 meters with the top speed at 8 meters per second. When getting the drone, you have multiple options. The first one is regular pack and the second one is jumbo pack. There are also 2 types of Tello drones. One is regular and the other one is EDU, which is the educational. This course is compatible with both types of drones. If you get the regular pack, it will come with a single battery, extra propellers and the propeller guards. The charging would be done connecting a USB cable directly to the drone. On the other hand, if you get the Tello Jumbo pack, then you will get everything as before, plus 2 extra batteries and a 3-slot battery charging hub. The Jumbo pack is much better for programming because with 3 batteries you can do a lot more testing, and while you are using one battery, you can charge the other one so that you do not have any delays. So first we are going to go to App Store or Play Store and we are going to search for Tello. Now once we find it, we are going to install and open it up. Now the first thing we will do here is to connect the Tello device. So we need to turn it on. You will see the lights, and once they stop blinking with all these different colors, it means it's ready. And there you go. So now it's blinking and it is only one color, so it means it's ready. So we can go to our app and we can click on Connect Tello. And then we are going to go and connect to our Wi-Fi. So here we will connect to the Tello. Once that is done, we will go back. Now we can see the live stream from our Tello device. So here you can see the live stream, and now it means that it is running. So once you have the Tello working, you will go to Settings and you will go to More, and here you have to make sure that your firmware is up to date. So here you will see firmware version and you have to click on Update. So it needs to download first, so you will have to connect your Wi-Fi again. You will have to remove the Wi-Fi of the Tello and you will connect to your home Wi-Fi and you will download the firmware, and then once it's downloaded you will go back and upload it to the Tello device by connecting it again. So here you can see it's already the latest firmware. If it's not the latest, it will allow you to download, and once it's downloaded you can upload it to the Tello drone. Once everything is set, we are going to try to run it to see everything works fine. So we will click on the takeoff button and we will slide to take off. And now you can see the drone is flying, so we can go forward, we can go backwards, we can rotate back, and then we can go up, and then we can go down. So I think I am about to hit my sofa, so I better get back. Now one thing you have to note here is that even though this is okay, we have 2 options here: tap to land and then hand landing. So most of the times when you're programming, you will be working with tap to land. Okay, so I want to mention here one thing which is very important. Even though this is an indoor drone and it is very suitable for indoor flying, you have to be precautious when you are running this drone. So It has a lot of safety features, but still you have to take care, especially of your surrounding. You have to be mindful of where others are, and you have to be mindful of where you are so that nobody gets hurt. So once this is done, we can go to the installations on our computer and we can start programming this drone. To program this drone, we are going to use the Python programming language. Now, to do this, we are going to first install Python, and then we are going to use an IDE, which is an integrated development environment, to actually write our code. So we will first go to python.org, and over here we will go to the download section, and you can download the latest version, or my recommendation is to download the 3.7.6. So that is the most stable version that I have found to work well. So you can go to all releases, and over here you can find 3.7.6. So you can download this, and then you can go to the PyCharm download section. Here you can see you have for Windows, you have for Mac, you have for Linux, and here you can download the community version, which is free and open source. Now, if you want to understand the IDE a little bit more, you can think of it like a notepad but with more functionality. So whenever you are writing the code, it will tell you where you are making mistakes, it will help you debug the code, and overall it has much more functionality than a regular notepad. So this is why we need the IDE. So one of the most famous IDEs for Python is PyCharm, so that's why we will be using this. Now the thing is that I have already installed both of these things on my computer, so I'm not going to do that again, but I have the footage from one of my previous courses, which was about OpenCV Python course. So it follows exactly the same procedure. So I will show the footage of that right now, and you can follow the same steps. The only difference will be that when you are naming your project in PyCharm, name it something like Tello course or Tello programming course or something like that. So let's start with the installations. First, we will go to python.org and we will go to the downloads section. Here we are not going to download the latest version. Instead, we are going to download 3.7.6 as this works well with OpenCV. So we will click on download, and then we will head on to the Windows version. Now, if you have Mac, you can download the Mac version as well. Once the download is complete, we will install. Make sure to add Python 3.7 to the path. So once the installation is done, we will close the dialog and head on to PyCharm. So we will head on to its download section and we will download the community version as it is free. Once the download is complete, we will run the installation file. Here we will associate the .py files to PyCharm, and we will also add launchers directory to the path. Next, we will restart the computer and run PyCharm. So now we are going to create our new project. Here, before we start the project, we will look into the project interpreter. Now this has to be 3.7. So if it's automatically detected, then we are good to go. So let's write down OpenCV Python and hit create. So now this is the PyCharm environment. Over here we have the area where we will write the code, and on the left hand side we have the project files and the project folders. So once the installations are complete, we are going to create our project. Now I have named it Tello course. So it will come with this main.py file. We can write in this file, or we are going to create a new one in which we will store all our code. So we can delete this one. We can right click and we can go to new and then Python file, and here we can say basic movements. Now to actually program the Tello, we need its library. So to install that, we will go to file, we will go to settings, and then we will go to the project, then the project interpreter, and then we will add. Here we are going to write DGI Tello. And here you will see that we have the DGI Tello Py library. So we are going to click on that and we will hit install. Now while this is installing, let's have a look at who actually created this library. So let's go to the link, and this is the guy. His name is Damia Phonitis. He's the one who created this DGI Tello wrapper, which is the wrapper for the original DGI Tello SDK. So what this does is it makes it a little more easier to communicate with the Tello and to command all of these different things and to perform different tasks. So there is a documentation for it as well. This is an example. So you have to import the library, and then you have to say connect. You can say move left, move right, move forward, and you can give it some values. So a big thanks to the guy who actually built it and all the contributors who have contributed to this GitHub repo and have made it easy for us to use the Tello library. And the license for this is MIT. So this basically allows you to use it commercially. You can modify, you can distribute, but you have to make sure that you include this in the distribution. So this is the license. If you are distributing, you have to add this to the license as well. Okay, so that being said, let's go back, and now you can see it's already installed. Now another library we will be needing later on is the OpenCV library. So we can install it now. So it's called OpenCV Python. We can click on that and we can hit install. And this will install both of these. And now you can see we have all these new libraries that we did not have before. So we can hit OK. And now we can go on to our coding. And first of all, we are going to import our library. So here we will write from DGI Tello Py import Tello. And then we will be needing the time as well. So we will write from time import sleep. So we want to add some delays between each command. So that is why we need this. So to connect to our Tello is very simple. All we have to do is we have to create a Tello object. So you can call it anything. I like to call it me. So me is equals to Tello dot Tello, Tello, and this will create our Tello object. And now we can simply write me dot connect. And this is how simple it is. You have to just write me.connect and it will take care of all the IP address and all the communication part for you. All you have to do is you have to run this. And to make sure that it is running properly, we will print out the battery. So how much battery do we have on our drone? So we can write here me.get battery underscore battery. So there you go. And if you are wondering where am I getting all these functions from, so you can click on control and then you can left click on your mouse, and this will take you to all the functions that you have available. So you have get height, get temperature, get altitude. You have all these different things that you can use. Okay, so that being said, actually let me show you more. You have flip left, you have move back, you have to give the X value. The X value is basically in centimeters. So this is 20 centimeters to 500 centimeters. You have move forward, move right, but we are not going to use these because this is very simple And you can use this in one of the third-party apps as well that move forward for 10 centimeters, not 10 actually, let's say half a meter, then move half a meter to the left, then rotate 90 degrees. All this stuff you can do with third-party libraries. What we will be doing is we will be using the RC command, and I will show you later on what that does. But before we go there, let's run this and see what happens. So we will right click this and we will hit run. But before we do that, we have to make sure that the Tello is connected to your Wi-Fi. So we will turn on the Tello drone and then we will go to Wi-Fi and connect. So I have turned on the drone right now, and then we will go to the Wi-Fi settings, and here we should have the Tello drone pop up. There you go. So now it's connected. I have pressed automatically connect. That's why it connected automatically. So once that is done, we can go back and we can right click and run basic movements. So if we run that, we get the response. First of all, we connected, so we got the response okay. And then we asked for the battery, so we got the response as 61. So right now the battery of my drone is 61%. Okay, that being said, now we need to see how we can control our drone. So as I mentioned before, you can simply write, for example, go forward. So if you wanted to go forward, you can write me dot go. Is it go forward or is it just forward? Move forward. So it is me dot move forward. So again, all these functions, you can read about them. So it tells you Tello fly forward with distance X centimeters. So you have to give a distance here. So you can write here, go forward, for example, 30 centimeters. And then you can write 50 centimeters and so on. But we don't want to do that. What we want to do is we want to control the speed. So as we discussed in the introduction, the drone can translate in 3 directions and it can rotate in 1 direction. So we want to control that. So we will write here me dot send underscore RC control, and inside that we are going to give in the 4 figures that we were discussing. So first of all, as you can see here, it says left right velocity. So let's say this is 0, and then it will say forwards and backwards. Let's say that is 0 as well. Then we have up and down, let's put it as 0, and then we have the yaw velocity, which means how much it wants to rotate. So all these speeds we have, and if we click on it and if we go there, you can see here this is the left right velocity. We have forward backwards, up and down, and yaw velocity. So all of these we can use from -100 to 100. So if we want to go forward, we will write, for example, 50, it will go forward. We will write -50, it will go backwards with half the speed. So we can go back here and let's write here, let's go forward 50. Then we will give it a delay. So we will write here sleep for 2 seconds. And then we are going to tell it to land. So we will say me dot land. Now, one thing that I did not write earlier was the takeoff. So before we actually send the command, we have to make sure we are asking our drone to take off. So we will write here me dot take off, and then we can send our command, then we can sleep, and then we can land. Now, if you want to land properly, and if you don't want the drone to be going forward while it's landing, then you have to repeat this and you have to write 0 over here as well. Otherwise, the drone, when it's landing, it will be going forward as well. So first we will stop it completely and then we will ask it to land. So it will land like a helicopter rather than an airplane. So let's try this out and see what happens. So as you saw, it took off, it went forward for 2 seconds at the speed of 50 and then it landed. So now we can move the drone towards the right as well. So we can copy this, and as we know, the first one is basically left and right. So we can change this to, let's say, 30, and let's see what happens. So as you saw, the drone first took off. It went forward for 2 seconds, then it went towards the right side for 2 seconds, and then it landed. So if we write here -30, it will go towards the left. If we write here -50, it will go backwards. So this is the basic idea. And if we want to rotate, we can rotate it. For example, we can say over here, we can say 30. And let's try this out, what happens. So as you saw, the drone first went forward and then it took a right turn. So this time it is in the yaw, not actually the right side, and then it landed. So these are the basic movements that we can control. We can control up and down, left and right, forwards and backwards, and we can control the yaw. If you like the video so far, give it a thumbs up and don't forget to subscribe. So now we are going to learn how to capture image from our drone so that we can process it and do lots of different experiments on it. So we will go to our Tello course and we will create a new file, and this file we will call it image capture. And the easiest thing to do is just to copy the standard, you can call this the boilerplate for the Tello drone. You can copy that, and now we can continue with our code. So the image acquisition part is not that hard. What we have to do is we have to write me.stream, and we will turn this stream on. So this stream will give us all the frames one by one, and we can process them. Now, because it is a continuous number of frames, we have to use a while loop. So we will write while true, and here we are going to write that our image is equals to me.getFrame, get underscore frame underscore read, and then we are going to write dot frame. So this will give us the individual image coming from the Tello drone. And now what we can do is we can resize this image if we want to process it faster. So to do that, we need to import our OpenCV library. So we can remove this. This time we are not going to use it. So we can write here import CV2, import CV2, and at the bottom here we are going to write image is equals to cv2.resize, and then we are going to give in our source image, which is img, and then we have to give the size we want to resize it to. For example, we can say 360 by 240. So we are keeping it small, the size of the frame, so that it is faster. So we can format this, and then we can write here cv2.imshow. So this is so that we create a window to display this result. So we will write here imshow, and then we will write here image, and we will say this is the name of the window, and then what do we want to display? We want to display img. So this is the idea, and then we are going to write cv2.waitKey. Now we are writing a wait key because if we don't write this, the frame will shut down before we can actually see it. So we have to give it a delay. So we are giving it a delay of 1 millisecond. So this should work well. And actually, let's do one thing. Let's remove this for now. And let's try it without the resize, and then we will try it with the resize. So let's right click on image capture. Now again, we have to make sure that the Tello drone is connected. Now it has already turned off for me because I didn't turn it on for a while, or I didn't use it for a while. So let's wait for it to connect. Okay, so now that it is connected, let's go to image capture, right click it, and we will run the image capture. So we have the 40% battery left. For image capture, it should not be a problem, and there you go. So this is the stream coming from my drone at this point. You can see, there you go. So right now it's 1280 by 720, and what we can do is, if we resize this, it will become quite smaller. So there you go. So now it's much smaller, and you will get some warnings here. Don't worry about these. As long as you're getting the frames, it's fine, and you will see a delay in the frames. Now this is because of the transfer, and this is because of the viewing. In reality, this delay is not that much, but because we are viewing it, we are continuously trying to perform all the graphical computations. That's why it's giving us this delay. So normally we will keep it at this size so that the processing is a little bit easier, and it will be a little bit faster with all the different functions that we use. So now we are going to use our keyboard to actually fly the drone. To do this, we need to get the commands of the keyboard first, and then we can implement it with our basic movements, and we can run them together. So to do this, we are going to create a new module called key press module. So a module is basically a piece of code that can run individually, and it can run from another script as well. So if another script wants to use its functions, it can do that as well. So we will create our module. We will write it as key press module, and we are going to use Pygame to actually get the commands from our keyboard. So we are going to import Pygame. Now the thing is that it has already been installed by default. So here you can see when we installed the other libraries, Pygame was also installed. If it's not there, of course you can go to add, and you can write here Pygame, and you can install that. So we will write here import Pygame, and then we will initialize a window for our Pygame. So initially, the idea of this library is to create different games. So whenever you want to detect a key press, it has to be within a game window. So we need to create that window. So we will create a new function called init. We are going to initialize our Pygame dot init, and we will write that our window is equals to Pygame dot display dot set mode, and we are going to give in our size. So this size can be anything that you want. So let's say 400 by 400. And then we are just going to call this function. So let's call it here. So we are going to, whenever you are creating a module, you will write if double underscore name is equals to main. Now this just means that if I'm running this file as the main file, then do this. Otherwise, no need to do this. So we will write here init. So let's see if that works. I have to write double equals. Okay, so let's run this. And there you go. So you saw that this window came up and it went away. So what we can do is we can initialize, and then we will update our window and it will stay, but for now we will move on. So what we need to do is we need to get the key press, and to do that we are going to write, by the way, you don't have to understand this whole part. You can think of this as just a function to get the key presses. So if you don't want to get into the details, you can skip this part as well, but it is recommended that you understand how we are getting the key press. So we will write here, for example, get key. This will be our function that we will call from a different script, and when we are calling the get key function, we can, for example, write here the key name. So we want the left key, we want A, we want S, whatever key we want, we can write here. So we are going to have a final answer, so we will call this and we will write it as false. So by default it will be false, and we are going to return this answer. So if the key is pressed, it will return true. If it's not pressed, it will return false. Now, without going into too much detail, we are going to write a few lines of code. We will create a for loop and we will check the events. So we are getting all the events and we are not specifically doing anything with them, so we will just pass. But then we are going to create our input. So we will say key input is equals to, now to actually check whether it's true or false, it has to go in a certain format. So we need to create that format. So here we are going to write pygame dot key dot get pressed, and then we will write here my key. So this is that format I was mentioning. So we will write get attribute and we will write pygame, and it has to be in this format. So it has to be k underscore, and then within the brackets it has to be the value of that key. So here we will write format key name. So what this will do is it will write it like this. So for example, if we say that our key name is, let's say, left, so it will write it like this. So this is the format that we need. So this is what we are doing. So once we have the correct format, we can now just check if key input my key, then we will write answer is equals to true, and what we will do, okay, this needs to be input, okay, and then here we will just update our pygame screen. So we will say display dot update. Now the reason I'm not going into too much detail with this code is because this is not part of the programming for drones. It is just acquiring the keystrokes. So there are multiple methods, there are multiple libraries you can use to do this. So I'm not going to go into the detail of how this works. If you want to know more, you can check out my other videos where I have explained these. So this part here, now we have created a module, and if we call in our get key function and we give in a key name, it will tell us whether it has been pressed or not. Let me format this. And what happens is that we can write a main function here to test it out. So for example, we can write main, and inside that we can write, for example, if get key. So this is how you can get the key, or let me just print it out for you first. Get key, let's say we want A, and over here I'm going to print this. So what we can do is we can write here while true run main. Okay, so basically first of all, the code will go here. It will check if this is the main file we are running. If we are doing this, yes. If that is the case, it will initialize, it will run this code, and then it will create this loop and it will keep running main again and again. So when it runs main, it will check get key A. It will do all of this processing. It will check whether it's pressed or not, and it will give us the answer back. So it will be either true or false. So let's print it out and see what happens. So if I run this, this is my Pygame window, and you can see now it's staying, and right now it's saying false. But if I press the A key, nothing happens. Why? Yeah, it has to be on this window. So you have to click it and then you have to press. Now you can see when I press, it actually changes to true. So this is a common mistake. Sometimes I forget as well. You have to be on this window when you press the button. So this is the idea. So here we can write, for example, if get key, let's say, is left, I think it's capital letters, left, then we can print left key pressed. Then we can write if get key is, let's say, right, then we can print right key pressed. Okay, so let's run this. So if I run it here, right now nothing is been print. So if I press the right key, it will say right key pressed. If I press the left one, it says left key pressed. So this is how it works. So what we can do now, this is a module. So if we run it by itself, this will run over here. But we can use only this function and this function. So what we can do is, we can go to the Tello course, we can create a new file, we can go to Python, and over here, let's call it keyboard control. So here, what we can do is, we can import this module. So let me close the previous ones. So this is our module. So we can write here, import key press module as KP. So the reason we are writing it as KP is so that whenever we use it, we don't have to write the whole spelling. We can just write KP. So what we can do right now is we can write kp dot init. We will initialize it. This is that init function. And then we will write kp dot get key. And let's say we want to get the key S. So we can print this out. So let's print it out. So now if I run this part, it will create that. Now the thing is, it only ran once and it gave us false. So what we have to do is we have to create a while loop if we want to run it again and again. So we will write true, and then we will put this forward, and then we can run this. There you go. So now it's saying false, and if I press the S key, it says true. So now you can see that we created that module, and we are able to use that module in other scripts as well. So, oh, the previous one is also running. Anyways, so what we will do now is we will attach this to our Tello, and we will, using these keys, we are going to move it. So let's write down the code for our Tello drone first. So we will write here from DJI TelloPy import Tello, and then we can write here from time import sleep. Okay, and then we will write here me is equals to Tello dot Tello, and then we will write me dot connect. And of course we can check the battery. It's always good to print out the battery to know everything is working fine. Okay, so this is our initial part. Once that is done, we are going to take off. So we will write me dot take off, and then we are going to write our code inside here. So let's remove that, and we will write here that, let's say, me dot send RC control, we are going to send in 4 values. So for now we are going to put them as 0, and later on we will add something to it. Okay, so what we need to do now is we need to check if the button or the key has been pressed. If it's pressed, then we will change this values, so based on which of the keys were pressed. So we can write a function here to check the key presses. So let's call it get keyboard input, and here we are going to define our parameters. So this is left and right, then we have forwards and backwards, then we have up and down, and then we have yaw velocity, right? So we will put all of them as 0, and then we will check each one of them. So we will write if kp dot get key left, okay, it has to be capital left, then lr, which is your left right, is equals to -50. So this is a speed that we are just giving, so we can change this if we wanted. So actually we can write a variable here, speed is equals to 50. So instead of writing speed every time here, we can just write it here. So this negative means it will go towards the left side. Now if we wanted it to go towards the right, we can simply copy this part and we can say else if, and we can change this to right. Again, this has to be right, and then we can remove this. Okay, so this is how you can do for one of them, and the same thing will happen for the rest of them. So let's say this is for up and down, so we will write here up and down, and for up and down we have to use up, which is the up and down. Okay, it should not be up, it should be ud, up and down. So let's write it d over here. So here when it's going up it will be positive speed, when it's going down it will be negative speed. So this is how you can do that. And then we will write, now we are left with the forwards and backwards, and we are left with the yaw velocity. So what we can do is we can write the same thing here, copy that, paste it here. The reason I don't like to write it like this is because this is very easy to read. Now the correct method, or the standard you can say, is like this, but I like to keep it in one line if it's just one line function, one line if statement. So I like to keep it like this so that it's very easy to read what is happening. Okay, so then we will write here W and we will write here S. So we will use the WASD keys. So here we are going to use, okay, so I think up and down will be easier to be used if we are using it with forwards and backwards, because normally with up, down, left, right, we are going forward, backwards like a car. So I think it will be better if we use here forwards and backwards. And here we can use up and down. So W is up, S is down, and then we can use the A and D. So A is towards the left side and D is towards the right side. So something like that. So I'm not sure about the rotation here, which is clockwise, which is anti-clockwise. So if it's not the right one, we can switch the values here like this. So let's keep it to this, and if it's not right, we will change it later. So all of these values, yeah, I forgot to change this. This should be your velocity, and this should be your velocity as well. So all of these values are now ready, and what we can do is we can send it back, and we can write here return, and we can return all these values. So all of this will be in a single list, and what we can do is when we call this function get keyboard input, the output of this will be, let's say, values. So this will be a list, and we can just send the values of this list here. So values at 0, values at 1, values at 2, and values at 3. So this will directly send all the commands, and what we can do is we can add a sleep here just to make sure everything is stable, nothing is happening too fast. We can control this. And what else? One more thing about safety is that we should be able to land with a key press as well. So let's keep it close. So we can copy this line and we can paste it here, and instead of A we can write Q, and if we press the Q button we want to land, so we will write here me.land. So this will allow our drone to land if we press the Q button. So we could add a button for takeoff as well, but or should we add or should we not add? Let's add a button for takeoff as well. So let's copy this, and we can write here take off, and we can remove the takeoff from here, and let's say that takeoff button is E. Did we use E? No. So let's put it as E. So E will take off, Q will land, and then the rest of them will be used to move forwards and backwards. So this being done, now we can turn on our drone. I think I need to replace the battery. So let me replace the battery and let's try that out. So let's connect to Tello. It's already connected and I think it should be fine. Let's right click and run. And there we go. So it is sending the commands and the response. We have 93% battery. Okay, so I will run this now and let's see what happens. So in the previous chapter, we had a look at how we can control the drone with a keyboard. Now in this project, we are going to create a spy drone or a surveillance drone. in which we can control using our keyboard, and whenever we require, we can take a picture of that environment and save it to our computer. So at any given time, we will be able to see where we are flying, and we can take any picture whenever we press a button. So here we can right click and create a new project. We will call this project, let's call it projects, and then we will write here keyboard control. What else should we write? Let's write image capture. It's a long name, but anyways. So this is basically our idea. First we are going to import. So we are going to import everything from our keyboard control. So this is the code that we wrote in our previous chapter. So we will copy all of that, we will close it, and we will paste it here. So over here we are going to make some changes, and what we will have to do is we have to merge these two codes, the one we did for image capture and the one we did for keyboard control. So we will go to image capture, and here you can see that we have to first of all turn on the stream. So we will copy that and we will go to our initializations, and once we connect we will turn on the stream. Then in the while loop we have to capture the image. So this is image is equals to get frame, and then we are resizing it, then we are displaying it. So we will copy all of this and we will go back, and in our while loop we are going to paste it. Now this is pretty much doing the same thing as this, so we are going to remove this, and here it's giving us an error because we haven't imported the OpenCV library. So we will write here import CV2. So this will import the CV2, and now we can see that if we run our drone, it will display us the image as well. So let's try that out. Okay, this is the previous one. We have to run this one. I think it disconnected. I need to connect it again. Okay, so now it's connected and we can run it. And there you go. So this is the image that we're getting from the drone. We can go back to our Pygame window, and over here if we press E it will take off, and then I can go forward, I can go backwards, I can go left, right, up, down, I can rotate. So all of the things that we did earlier we can do again, but now we are able to see the actual footage. So this is great. So we can stop this. Now what we need to do is we need to store this image once we have pressed any button. So what we can do is we can create a new if statement here. So we can write if kp.get key, and we will write that, let's say it is the Z key. Normally it would be S for saving, but we are already using S, so we will use the Z key. So here we will write cv2.imWrite. So this is for saving the image. So now we have to save the image with a different name every time. If we don't do that, it will overwrite the previous image, and we don't want to do that. So here we are going to write a string. So we will write here, let's actually put it in the resources folder, resources, and then inside the resources we will put it in the images folder, and now we are going to give it a unique name. So how can we give it a unique name every single time? The simplest method is using the timestamp or the current time, because the date and time will never be actually the same. Even if you use maybe 1 second later, 2 seconds later, it will never be the same. So this way we can write here time dot time. So this will give us a unique name every time, and then we can write .jpg. Why is it giving an error? Let's check out, because we are okay. Let's just say import time. So hopefully that error will go away. Yeah, there you go, it's gone away. And now we are getting this error, so we can write here time dot sleep. Okay, so here we are getting our time, and then we are storing it as JPG. But what are we storing? We have to define that. We want to store our image. So the image that we are using here, we want to store that. So in order to use this inside this function, we have to make it global. So we will write here global image. So that should work fine. So let's run this and see what happens. So actually, before we do that, we need to create a folder here. So we will right click, we will create new directory. So our directory name should be resources. So we will write here resources, and inside resources we need to create another directory called images. So this is the directory we have to create, and once that is done, we can now run this. So again, it got disconnected. Let me connect it again. Okay, so now that it is connected, we can right click and we can run. And there we have it. So without actually running it again, we can press the Z button, and if we go to our resources and images, there you go, you can see there's a lot of images saved. And if I just right click and click on show in Explorer, there you go. So these are the images saved. Now the problem is, when I press the Z button, it clicked so many times and it saved so many times. So what you can do to avoid this is you can add a delay. So right after you press that, you will say time.sleep, and let's say for 0.3 seconds. So if I run this again, let's press the Z button, and this time if we go back, there's only one image. So we can stop this and we can go here, and there you go. So this is the image that we get. So let's fly it and see what happens and how we can get the images. Okay, so let's take off. Okay, we are getting some error. I think we need to reset the Tello Drone. Let's try it one more time. Yeah, it is unsuccessful. So we need to reset the Tello Drone to actually run it again. Yeah, the drone was actually turned off, so we have to turn it on again. And now let's connect and run it again. Okay, so right click and run. And there we have our Pygame. We can press the E button to take off. We can go forward. Let's rotate a little bit. Let's rotate back. Let's take the image of this sofa, and then let's move towards the right, and let's take an image of this chair. And let's move on the side. Let's take an image of this chair. And let's go back and we can stop it. So we will go to images and show in an explorer. And we have the previous image that we took from the previous run. And here we have the new images. So this is the sofa, this is one chair, and this is the third chair. So as you can see, we can fly around and take pictures, and they are getting one picture at a time instead of just having a lot of images at the same time. Okay, so this is good. So it's very simple. As you can see, you can gather together the different codes, the one we did for keyboard control and the one we did for image capture. You can merge them together to create an exciting project. If you like the video so far, give it a thumbs up and don't forget to subscribe. In this chapter, we are going to look at how we can map our drone. Now, this is also known as odometry. The idea here is that we are going to use the velocity information to find the distance, and we will also use the angular speed to find how much angle the robot has or where is it headed. And based on this information, we are going to get the X and Y coordinates. So we will take the distance and the angle and we will convert it into Cartesian coordinates so we can plot it in a graph. So let's have a look at the explanation of this before we actually go into implementing it. So let's say that this is a virtual grid that we have, and every time we press the forward button or we rotate, it can rotate only in these grids. So whenever we press one time, it will go forward, and then we press it again, it will go forward again. Now, what is the distance that it will travel? That we will calculate. So let's say that the speed of our drone, the one that we have been using in our previous chapters, let's say that is 10 centimeters per second. So that means that, for example, if we take the time as 2 seconds, then it will move 10 centimeters, then again 10 centimeters. So it will move 20 centimeters. So our distance will be 20 centimeters. So to convert this, it's very simple. We have 0, 0, and then when it goes forward, it has moved 20 centimeters. So the coordinates will become 0 and 20. So that's how simple it is. But let's have a look at what happens when we introduce an angle. Let's say that we do not move forward. All we do is we rotate. So let's say that we are just rotating. So we are rotating like this. So the idea is that we have our angular speed. So let me bring that back. So let's say that we have our angular speed as 45 degrees per second. So it means if we rotate it twice, so if we are here and if we rotate it twice, so it will rotate 1 second 45 degrees, another 1 second it will rotate 90 degrees. So this is what will happen. So now our coordinate is pretty much the same, 0, 0, but our heading is towards the east instead of north. So what can we do to actually find the coordinates when we are pressing both the forward button and the right or maybe the left button? So we are rotating and we are also moving forward or moving backwards. So how can we calculate that? So by the way, the angular speed is pretty much the same way that you would calculate the distance. So here, if you are moving, let's say for 2 seconds, so 45 degrees per second for 2 seconds will give you an angle of 90 degrees. So that will be your heading after 2 seconds. So let's look at how we can use this and how we can find our coordinates. So let's say we pressed the forward and we pressed the rotation button at the same time. So now the drone starts moving, but this time it will start rotating as well at the same time. So at the same time it's moving forward, at the same time it's turning. So it will start moving like this. So at the end of the day, it has moved, let's say 2 blocks, and then it has rotated 90 degrees. So how can we find these coordinates where it is now? I'm just assuming that it is here, but how can we actually find these coordinates? So what we can do is, let's assume that these coordinates, the final point is over here. So what happens is that this is our traveling distance. So this is basically, it will be a curve. It will not be going forward and then rotating. It is happening at the same time. So how can we find that? Well, in this case, let's say this is our final point, and this is after 1 second, and this is after 2 seconds. So let's say this is our curve. So what we will do is we will find the coordinates after every unit of time. So whatever distance we have kept constant, or whatever time period we have set, in this case we have 1 second. So after 1 second, we will look at what is our position. So let's say it is here. Let me place it a little bit nicer. There you go. So let's say that this position is over here. So then what we will do is we will find, first of all, we have the distance. So in the first interval, our distance will be 10. After 1 second, our distance will be 10, and our angle will be 45. So what we can do is we can write the equation where d is your distance, then d multiplied by cosine of 45. So d here will be the value of 10. So distance multiplied by cosine of 45, and then we will have the sine. So d here again will be 10. So this will be 10 multiplied by sine 45. So this will give us the y coordinate, and this will give us the x coordinate. So this way we will have the x and y coordinate over here. So the answer of this is about 7, and the answer of this is also about 7. So this point here will be 7 and 7. So if we just copy this, we can write here that this is 7, I think 7.07 and 7.07. So after, 1 second, this will be our coordinate. So we can place this dot in our actual diagram. And then again, we will, if we are moving with the same speed or the distance, and then we are moving at the same angle, then it will also have the same effect. So we will have 10 sine 45 and 10 cos 45 again. So this calculation we will do every single time after every block of unit that we have traveled. So it will be like this. And then again we will have the same calculation, but this time we will add our previous value to it. So because earlier we had 0, 0, so we didn't do anything, but this time we will add to it. So it will be 7.07 plus 7.07. So that will give us 14.14. So this coordinate here will be 14.14 and then 14.14. So if we are moving at the speed of 10 meter per second and the angular speed of 45 degrees per second for 2 seconds, after 2 seconds will be at 14.14 and 14.14 in our Cartesian coordinates. So this way, after every unit of time, we can measure and we can pinpoint exactly where we will be. So this is what we are going to do. So let's have a look at how we can implement this mapping method. So we will go to our new file and we will name it, what should we name it? Let's say mapping. Okay, so the first thing we want to do, a lot of this is related to the keyboard control because we will be the ones controlling on the keyboard, and when the drone is moving, we will plot it where exactly is it moving. So we will take the keyboard control, we will copy all of it, and let's remove the other ones, and we are going to paste it. So the first thing we have to do here is to write down our parameters. So as we have discussed earlier, we need the speed and we also need the angular speed, and from that we will calculate the distance and we will calculate how much angle do we have. Now first we are going to write the forward speed. Now the thing is that we already have the forward speed, the one that we are sending. So for example 50 means 50 centimeter per second. But the thing is that when I experimented with it and tried to find out my own values to see if it's correct or not, a lot of the times the values differed. So the Tello drone is not very repeatable and it is not that accurate, but still we are trying to learn the concept, and based on my testing I found out that if I move, for example, 10 seconds, I was getting a distance of 117. So 117 divided by 10, this is basically our speed. So I can write it here, forward speed, which is basically in centimeter per second. So this is the centimeter, how many centimeter it traveled, and this is how many seconds it traveled. So it traveled in 10 seconds, 117. And I was giving the speed of actual 15 centimeter per second. And you can see it's coming to about 11.7, around 12 centimeter per second. So again, doing some manual testing can help as well. And again, with the angular speed, I tested it out as well. So the A speed, let's write it capital here as well. The angular speed, it took about 10 seconds to rotate 360 degrees. So our speed will be, so angular speed in degrees per second. So this will be our angular speed in degrees per second. Now in the example, we took the interval as 1 second. So we were checking the value, or we were plotting the value after 1 second. Now that is a very long time. We don't want to do that. We will reduce the interval to actually, interval is equals to 0.25. So based on this information, now we have the speed and we have the interval. So every unit of our map will represent a certain amount of distance and a certain amount of angle. So that distance and angle we can find. We can write here that the distance interval is equals to forward speed multiplied by our interval. And then the angular interval is equals to A speed multiplied by interval. So this will give us the distance and the angle every time we move 1 unit. Okay, so these are basically our parameters. Now you can play around with these, you can try it yourself, you can time it using a stopwatch, you can write an actual code by yourself to test these different things out. But these are the values that I found to be a little bit towards the better side. So again, this is not very accurate, so don't expect it to be very, very good. But the idea is that if you understand this concept and if you come across a better drone, then you can use the same methodology to create a more accurate model. Okay, so that being said, what we can do next is we can try to actually plot something to see how the OpenCV actually works. So in order to plot, let's actually remove this. In order to plot, we are going to create an image and we will create a blank image. So we will call it image is equals to, and we will use the numpy library. Now, we haven't used numpy before. It's basically a mathematical library that allows all these different mathematical or matrix calculations. So we are going to import that. So we will say import numpy as np. So we are going to use that. So image is basically a matrix of pixels, a matrix of numbers. So that's why we can use the numpy library, which is known for handling matrices. So we can use that to call numpy.zeros. We want a matrix of zeros, and we want it to be the size of 1000 by 1000 by 3. So the 3 is basically the channels, so we wanted a colored image, so that's why we have RGB channels. And here we will say that the values that are stored in these matrix, they are basically unsigned integers. So that's how you write unsigned integer, and it should be 8-bit. 8-bit means that we can have a value from it means 2 to the power of 8, 2 to the power of 8, which is equals to 256. So therefore our values will range from 0 to 255. So these are the values that will be stored here. Okay, so that being said, let's draw something on it. So let's create a function called draw points, and we will call this function whenever we want to draw. So right now we will just draw something simple. Let's just draw a circle. So cv2.circle, and we are going to give in our image, so the image that we want to draw the circle on. Then we will give our points, so let's say 300 and 500. And then we are going to say that our, I think the next part is size. Let me check. Radius. Wait, it's not supposed to be radius. What is happening? Is cv2 imported? Oh, it's not imported, that's why. So import cv2. Let's try now. Yeah, there you go. So now it's telling us what is required. So the next thing will be radius, then color, then thickness. So radius, let's say 20. Color, let's say red. So let's write 0, 0, and 255. So it's BGR. In OpenCV, we don't use RGB, we use BGR. So this is blue, green, and red. And then we are going to say thickness, we want to fill it. So we will write here filled. So, oh, I wrote it wrong over here. That's why. Okay, so we can do a little bit of formatting here, and okay, let's run this and see what happens. Oh yeah, we didn't actually show anything, so we have to show this. cv2.imshow, and we will write the window name. So let's say output, and then we will write image, and then we will write cv2.wait key to have a delay in between of 1 millisecond. So let's run this, and there you go. So this is our output screen. It is 1000 by 1000, and you can see the circle is drawn over here. So we can make it a little bit smaller. It's really big. Let's make it 5, let's say. And there you go. So now this is a dot, and if we keep adding more dots, then we can create our plot that we need. Okay, so now what happens is that we have to find the value of how far we have traveled. So let's call this, these are our final values. Let's call them x and y. So we will keep it very simple. We will call them x and y. So here we will say x and y. Both of them are 500. So actually, let's write it at the top. So the idea is that at any given point, we want to plot this x and y. So we can simply go here and we can say, instead of this, we can say y and we can say x. That's it. So if we run it now, it should plot right in the middle. So this will be our starting point. And then whenever we press a key, this x and y value should change. So what kind of change that we have to put here? So let's have a look. So let's look at the left first. So here what we will do is we will add to our distance, and then we have to add to our angle. So at any given instance, whenever we press the key, we have to check the angle and the distance. We have to update them. So this is the final value in the x and y coordinate, but there should be another value which is basically the distance and the angle, and we will check every time what is happening to them. So the angle we will keep the same. So the angle should not be reset to 0 every time because it will continue to add on, but the distance we will reset every time. So we will write d equals 0 here inside and a equals 0 outside. Okay, so now we need to update this whenever we press a key. So for the left, we will update our interval. So we will write here d is equals to our dp, our d interval. So normally, whenever we are traveling with this distance, but we are not traveling in the forward direction. We are traveling towards the west. So we have to change our angle. So we will put the angle as minus 180 degrees. Now for the right, we will copy this. For the right, we are going to change our angle, and the angle will be 180 degrees. And our distance will be negative. Then we will go to up. Now for up, our interval will be positive, but our angle will be towards the north. It will be 270. And then for down, our angle, so this is not actually up and down. It is basically forward and backwards. So for that, we have to write that our interval is again negative, and then our angle is minus 90. Okay, so this is basically simple because we are just moving left, right, forward and backwards. But when it comes to actual yaw rotation, then it gets a little bit tricky. So we need to change the angle. So here what we will do is we will check our previous angle and we will add to it. So A will be that our yaw is equals to plus equals to our A interval. So it will not just be a new value, it will be added to our previous value. And in the other direction, we will remove it. So we will write here minus A interval. Now we did not declare yaw, so we need to declare that. And we will write here yaw is equals to 0. And we can write here, let's say global yaw. Okay, so after doing that, now we have updated all the values we need to update. Now we need to convert it into Cartesian coordinates. So here we are going to update our angle. So angle will be plus equals the yaw, and then we are going to get our x and y. So finally we will write x is equals to, actually plus equals to, because we have to add it to our previous value. Initially it will be 0 0, then it will be added. So we will write here integer, and then we will write the distance multiplied by the math dot cosine. I think math is not imported, so we need to import here, import math. And if we go down, okay, so math dot cosine, and then we will write math dot radians, because this function actually uses radians, so we have to convert it into radians. So math dot radians, and then we can enter the value of a. So there is a problem, most probably because of brackets. This is for this, this is for this. Oh no, it's the spelling. Okay, so is that good? There is still an error for some reason. Math dot cosine, math dot radians, a, and then okay, the problem I think is because x is not global, so we will put it as x and y. There you go. Then we can copy this and we can paste it down here, and we can say that this is y and this is sine instead of cosine. So do we need to change anything else? No. So this seems fine. So what we can do now is we can send this x and y over here. Now it's already been sent, it's already been updated, so we don't really need to worry about the points, but we could actually write it from here. We can send it back from here, and then from here we can send, let's say, our image that we want to draw on, and we can send the points. So we can do this, but it should work automatically as well, but this is a better way to do it. So we can write here points, and our points is basically points is equals to the values at 4 and the values at 5. Okay, so let's run this and see what happens. Point 0 and then points 1. So let's run this and see what happens. Okay, we get an error. Local variable a referenced before assignments. Where is a? So this needs to go here. Let's try it again, and there you go. So this is our Pi game. We have to click here in order for it to run. Whoa, that goes really fast. Okay, so it's going back and forward, and then is it rotating? Yeah, kind of. Okay, so it is working, but there is an issue. What is the issue? Let's try to find out. Okay, so the first thing is that I forgot to add the delay. So if the time is not accurate, then all of our calculations will be wrong. So we need to write here time.sleep, or I think we imported sleep directly, so we can write here, for example, 0.25. So this has to be exactly the same as the interval, so we will copy it from here and we will write it here. So this has to be our interval, and now it will be not that fast as before because of that interval. So let's try it out. Yeah, so now it's much slower and it seems much better, and you can see now it's rotating as well when I press some keys. But again, the problem is that we cannot see the path, so it's always printing this point, but then we don't just want this point, we want all the points that have been plotted since. So what we can do is we can create points. We can go here and we can write points, and we can put it as an empty list. Then we can go down, and instead of sending these values directly here, what we can do is we can append. So we can say points dot append, and we want to append these values. So this will keep adding to the points. So let's, and the other thing we have to do is here again we have to loop through these points, and then we have to print them out, or we have to draw them. So we need to add a loop here. So we are going to say for points in points, we are going to write point at 0 and point at 1, or we could simply write point as well. It should work. So let's run that and see if it works. We get an error. Argument is not a tuple. Okay, so which line is it? Okay, I think we just need to change the brackets here, because those are for a list. So hopefully this will work. Yep, okay, so there you go. And now if we click, and there you go. So now if I move forward, you can see I have kept the forward button pressed, and now if I press D, you can see it's rotating, but it's rotating in the wrong direction. Okay, so now if I press A, you can see it's moving, and if I press left, it's going left. If I press up, it's going up, and it will give us the estimate. So we can simply print out the value of X and Y, and that will be the coordinate, or that will be the distance traveled. So we can print it here. We can say cv2 dot put text. We'll put it on the image, and we can write the points. So we will write here F, and then inside that we are going to write a bracket right here, points. We are referring to this and not this. We are outside the loop, so we will write points, the last one. So we want to put this text at the very end, so we will take the last value and we will take the 0 element of it, which is the X, and we will subtract 500 from it, because our starting position is 500, so we will subtract 500 from it, and then we will divide it by 100, so that we are giving the value in meters and not centimeters. And then we have to write the other one. So the other one will be pretty much the same thing. So we will copy that, we'll paste it here, and we are going to write -1, and over here we will write 1, and then at the end we are going to write meters. So that should be good. So this is basically the distance, or the X and the Y coordinate printed out, but now we have to mention where do we actually want to put this. So we need to define the points, the point where we want to put it. So we don't want to put it exactly on the same point, we want to shift it a little bit. So that's why we will write points, -1 and 0. and we will add 10 to it so that it goes a little bit forward. And then we can copy this and paste it here, and this time we will add, let's say, 30, so it is a little bit down, and we will make this 1. So we can format this like that. Let me bring it here a little bit. Okay, so that should be good enough. And there was another issue, that it was not rotating in the correct direction. So when I was pressing A and D, the values were reversed. So this is supposed to be plus and this is supposed to be minus. Okay, so that is one thing. Now another thing that we did in the previous, the keyboard control chapter, is that we wrote a single value here, the speed, as 15. But in this case we will have a different angular speed, and we will have a different the forward speed. So here we have to, either we can write it here or we can change it down here. So let's keep this as speed. So we will keep it at 15 because that is the speed that I used for testing, and the angular speed I used was 50. So I used 50, so we can write A speed is equals to 50. So we don't need to change this, but we need to change this down over here. Oh. So there you go. So now if we run it, okay, something is missing. Oh yeah, we didn't complete it. We didn't complete this. There is a font missing, so we have to write the font. cv2.font plain, and then we have to write the thickness. What else? Then we have to write the color. We forgot a lot of things. 2550255, and let's put the scale as well. So this is the scale and this is the thickness. So let's put a comma there and let's run it. There you go. So right now it's saying 495 and 495. Why is it saying that? It should be 00 at this point. Where did I make a mistake? Points at -1. I think it's using 00 maybe. So we need to check here that if the points -1 at 0 is not equals to values at 4, which means it is the previous value, or the points at -1, 1 is not equals to values at 5. Now this just makes sure that we are not plotting the same thing again and again. Then we will append, otherwise we will not append. Okay, why is this giving? Okay, let's run it. Index is out of range. Index is out of range. Okay, so what we can do is we can give it some values in the beginning, so it is not empty. So we are just giving two values in the beginning so it can compare. There you go. But the value is still 495. Why is that? Let's check our value here. I think we need to add a bracket here, maybe. Let's run this. Yep, that was the problem. Okay, so now we have 0, 0, and let's move it forward. And there you go. So now we are getting the distance as well as the coordinates in both directions, and we are getting the map as well. As I'm moving it, I can see what is happening. So I can press these different keys and it will keep rotating, and at the end of the day it will tell me how far I have moved. So what I can do at the end is I can create another circle so that it is for the heading. So I can change the color for BG. Let's make it green, and let's make it a little bit bigger. So we will make it, let's say 8, and we will use the last points. So let's run it again. Okay, I'm missing something again. It's points. Okay, there you go. So now it's green, and if I move it, there you go. Now it looks much better. Gives us the estimation of where the drone is. So now let's test it out on the actual drone and see what happens. In this project, we are going to look at face tracking. So we will look at how we can make our drone to track a particular object or a face or even a full body. So we will do it with face tracking, but later on you can implement it with any of the other objects as well. So first of all, let's have a look at the concept. Now, when we have to move the drone and we have to track our face, we need two different things. We need the motion of forward and backward, and we need the motion of rotation. So we need yaw and forward and backwards. So let's have a look at forwards and backwards first. So we will treat both of these individually, and then we will combine the code for them. So let's have a look at the concept of forwards and backwards. So if the object or the face is looking small, then it means we need to move forward. And if the object or the face is looking quite big, then we need to move backwards. So we are too close, we need to go back. So if this is my drone and this red area is where it is too close and this red area is where it is too far. So both of them, the drone has to move. This green region is where you do not have to move at all. So let's say the person here, she moves backward. So now the drone will have to compensate and it will move forward. So it will go up till that green zone and then it will stop. Now let's say she moves forward. Then the drone will have to counter the movement by going back, and it has to go back until it reaches the green zone. So this is the idea that there will be a green zone in which the drone will not move, it will be stationary, and if it's too close it will go back, if it's too far away it will go forward. So this zone we are going to define by area. So let's say the area over here is 6,200 and the area over here is 6,800. So these are the values that I found after some testing. So we will be using these values to actually put in our drone. So this is the area. So if you take the number of pixels, so the width multiplied by the height, so you will get this value. So these are in pixels. Again, you can change these values later on according to your needs. If you're doing a full body, the area will be different than if you're doing a face or you're doing another object. So that being said, let's have a look at the yaw angle. So the idea here is that we are able to go forward and backwards, but what if the person starts rotating? The idea here is that we always want our object to be in the center of the image. So let's say this frame is the image that we have and the person is not in the middle. So then if they are on the left side, you will move the drone, you will rotate it, and this will bring the person in the center. And if, for example, if they are over here, and then you can rotate and this will bring back to the center. Now the thing is, we can give it a value. For example, let's say at this point our object is on the left hand side, so we will say rotate anti-clockwise direction with the speed of 20, let's say. So it starts moving at the speed of 20, and when it reaches the center, it cannot stop immediately. It will move a little bit forward because of the momentum. Think of this as a fan. So if you turn off a fan, it will not just stop immediately. It will keep rotating and after a while it will stop. So the same thing will happen here. So if we tell it go 20 degrees, go with the speed of 20 centimeter per second, and when it reaches the center, if we tell it to stop, it will not just stop immediately. It will go a little bit further. This is called overshooting. So the same thing will happen if, let's say, she's on the other side and then we do it here. So what happens is when it overshoots, the image will not be in the center, it will go here. Then it will try to retrieve and it will go here. So it will keep going back and forth and it will not stabilize. So how can we make it better? So we can make it better by reducing the speed as we reach our destination. So let's say the speed here is 20, and once we are getting closer, let's say the person is here now, then we will reduce the speed. Let's say right now it's 10. Then it will become 5. And by the time it reaches the center, it becomes 0. So this way, instead of having plus 20 and minus 20, it will have a value that will change based on how far are we from the distance or how far are we from the actual point. So this method is known as PID. I will not go into the detail of how PID works more than this. I think this is a very basic explanation that will give you a basic understanding. But if you want to learn more about PID, it's basically proportional, integral, and derivative. So these are the terms. It's type of a controller that you can use. You can relate two different entities together which are not relatable by default. So these things are a little bit complicated if you haven't seen them before. But for this course, this explanation is more than enough that it is able to go back and forth. And when it is reaching the center, it has to slow down. So we will be using this methodology in our implementation. So let's have a look at the implementation now. So we will first create a new file and we will call this face tracking. So this project is more towards OpenCV. So we will first look at the OpenCV part and then we will see the integration towards Tello. So let's import CV2 and then we will import NumPy as NP. So what we will do first is we will run our webcam. So I will be using my standard webcam rather than the Tello Drone, And once everything is done, we will integrate afterward. So I will write here cap is equals to cv2 dot video capture, and I have multiple webcams, so I'm using the number 1. If you don't have multiple webcams, most probably you will be using the number 0. Okay, and then we will write while true, we are going to get our image from cap.read, and then we will say cv2.imshow, and we will say that this is our output, let's say, and this is our image, and cv2.waitKey, and we will give a delay of 1. So this is the standard code for actually running the webcam with OpenCV. So let's run this and see what happens. So right click and run. So here is my webcam. So I will be using my image for the face tracking part, and once that is done, we will try out with the Tello Drone. Okay, so now the first thing we will do is we will track, or we will detect the face first. So we will create a new function and we will call it, let's say, find face, and we want to find it in an image. So we will pass that image that we want to find it in. And to find these faces, we are going to use a method proposed by Viola Jones. So this is a very famous method of using Har cascades. So this is basically a file that has all the parameters and information of a model that helps us detect different objects. In this case, the file that we have will help us detect faces. So let me copy that file. So this file is available on the official OpenCV website, and it is also available on my website under this course. So you can download it from either of the places. So you can go to resources, and we are going to paste it here. So the name of this file is Har Cascade Frontal Face Default. Actually, we are going to click on rename, and we will copy this name because it's too long. And now we have to refer to this file. So we will say that face cascade is equals to cv2.cascade classifier, and then we are going to write in the image path, this file path. Now this file is inside resources, so we have to write here resources, and then we can write the link or the path of our file. Then we are going to convert this into grayscale. So we can do by writing cv2.cvt color. Now, if all of this is overwhelming for you, what you can do is you can go back and check out my OpenCV course. It has been very popular. It has more than 1 million views now with 99% positive feedback. So if you go through the OpenCV part, this stuff will be very easy for you. But if you don't have a lot of background with OpenCV, then just take my word for it that, for example, this line is for converting to grayscale. So then we will write image and then cv2.color underscore bgr to gray. So this will convert it into gray, and then we will detect all the faces. So we will write faces is equals to face cascade dot detect multiscale, and we are going to pass in our image, so the gray image that we just did, and then we are going to pass in some parameters. Now these parameters, normally the first one is basically the scale factor, and the second one is the minimum neighbors. So what you can do is you can play around with these values. The ones I found to be good are 1.2 and 8. So again, you can read about these by going to their default function, or you can check it on the online documentation. I will not be going into that much detail here. So then we are going to create a list of all the faces, and then we will create a list of all the areas of these faces. So there can be multiple faces, so we need to find the biggest one, and we will assume that that is the one we want to track because it is the closest one to the camera. So we will detect that one. So we will write here my face list is equals to empty, and then we can write my face list area. Actually, let's write here C for center. So this will have the information of our center point. So CX and CY, where is our face detected, and this will have the area value. So these will be two lists, and then we will create a for loop. So we are going to write for X, Y, W, and height. So basically, whenever it detects these faces, it will return us these values. So we can unpack these values within this faces. So we can write XYZ in faces, and then we will write that we want to draw the rectangle around this face. So we will write here cv2 dot rectangle, and for the rectangle we have to send an image. We have to give it the XY coordinate, and then this is the starting point, and then we need the ending point. So the ending point will be X plus width, and then Y plus height. Then we need the color, so let's put it as red, so it's BGR, so 255 will be at the end. And then we have the thickness, let's put it as 2. Okay, so that is good. Now let's run this and see what happens. Let's try it out before we go any further, and we need to call this function, so we will call it by writing it here, and let's run it. So there you go. So now you can see the face is being detected properly, and it doesn't seem to be that bad. Even if I'm moving, it's sturdy and it stays there. If you don't find good results, you can always change these values to get something better out of it. Now once we have this, what we will do is we will get our center X and center Y. So we will write here Cx is equals to X plus width divided by 2, and then Cy is equals to Y plus height divided by 2. So once we have this, we can also find the area. Area is equals to width multiplied by height, as simple as that, multiplied by height. And then we are going to write that we want to append this, but should we print? Okay, let's just append it first. So my face list C dot append, we are going to append the value of Cx and Cy. Okay, and then we are going to append my face list area dot append, and we are going to append the area. So once we do both of these things, what will happen is, okay, let's print it first. So we can draw a circle at this Cx and Cy position so that we see where exactly is the center. So we can write here cv2 dot circle, and we need an image. What else do we need? We need the center. So the center will be Cx Cy, and then we need the radius. Let's say radius is 5. Then we need the color, so let's say 0, 255 and 0. And then we need the thickness. We will say filled, cv2 dot filled. We want it complete, filled up from inside, and that should be good. So let's run this and see what happens. And there you go. So now you can see the center, the value of the center is being displayed as well. So this value is what we will return. And but what we can do is, because right now we only have one face, so it's obvious we will return this value. But The reason we did these two lists is because we want to find the maximum area and we only want to send that value back. So here we will check if the length, before we actually do any calculations on this, we need to check if this is empty or is it filled. So if it's empty, there's no point of calculations. So we will check first my faces. We can pick any one of these. My faces area is not equals to 0. If it's it has some values inside, then we will say I is equals to my face area dot index. We want to find the index for it, and then we want to find the index of the max value. So the max value of our area, my area list. Okay, so this will give us the max value of our area, and this will give us the index of that max value. So once we have that index, we will say return image, and then also return the my face list at at I. And we also want to return the area because we want to use that. So from that list, we will use this index to find the maximum value of the area, and from that area we will get the cx and cy values of that corresponding face. But if this is not the case, then we need to return something else. So we will say else return the image, and then return 0 0 for the cx and cy and 0 for the area. So this will, we're pretty much returning nothing. Okay, so now what we can do is we can get the values. So we have image, and then we have, what else do we have? We have the cx and cy. We can call it collectively as info. So this will be the info that we will get back. And once we have it, what we can do is we can print it out. So we can write here info at, let's say, 1. This will give us the area. So we can write here area is info 1. So let's try that. And there you go. Now you can see the area being detected. So as we discussed in the beginning, in the explanation, if we go forward, the area will increase. If we go backwards, the area will decrease. So based on this, we are going to move our drone. Okay, so that is good. And then we also have the center value. So the center will be 0. Should we print it all together? Maybe it will be easier to read. So let's just print it here like that. So let's run it again. So there you go. So now we are getting the center values and we are getting the area. So the center values will be used to rotate, and the area value will be used to go forwards and backwards. So this is good. Now what we can do is we can introduce our drone, and we can also introduce the range. So let's do the tracking first. So here we will define a function. So we will say track face, and what we need is we need the drone, so the variable me, and then we need the info, and we also need the width and the PID and the P error. Now I'm going to explain all of what these are, so don't worry about it, at least for now. So what happens is that we need to create a range. So we are doing the forwards and backwards right now. So we need to create a range, So over here we are going to write that our forwards and backwards range is equals to, as I mentioned before, it was 6 to 800, sorry, 6 to 100 and then 6 800. So these were the values for our range. And then we are going to, where is it? And then we are going to write here that if our info, or should we call it area? Let's call it area so it's easier to see what is happening. Area is equals to info at 0. No, it was at 1. So if area is greater than the front, the forward and backward range at number 2, then we need to go back. So the forward and backward speed will be minus 20. Okay, so this is that. And then we can write else if the info, or not the info, the area is less than the forward and backwards range at number 0. This should be 1. Then we will say that forwards and backwards is equals to 20. So at this point it is saying that if it's too far, then go forward. If it's too close, then move backwards. Now we need to add a safety factor here, and the reason is that if we only say that the area is less than this value, which is 6,000 something, then 0 is also less than 6,000. So if nothing is detected, it will start going forward. So we need to mention here that and area is not equals to 0. So if it's not equals to 0 and it is less than our range, then move forward. Otherwise it will move backwards. And we also need to add a condition where it will stay stationary. So that should be the first priority, that if it has to stay stationary, stay stationary. So we will write here if area is greater than our forward and backward range at 0 and our area is less than our forward and backward range at number 1. So this is the idea, and then we will write forward and backwards is equals to 0, and we can make this else if. So now we have these 3 conditions. The first one is where we have the green zone, the drone will not move at all. The second one is where it is too close, it is too big, so it will move backwards. And this one is where it is too small or too far and it will move forwards. So now all we have to do is we have to send our command to the drone. We can send this FB value, forwards and backwards. That's it. Now let's have a look at the PID for our angle. So for the PID, we are going to introduce the error. So error is equals to, let's unpack our X and Y as well. So let's remove this, bring it here, and then we can say that our X and Y are basically info at 0. So here we will say that our error is basically the X position. So we will say that X minus the width divided by 2. So what is this width divided by 2? It is the center of our image. So we want to find out how far away our object is from the center. So this is the value of the object or the face, and this is our center. So when we subtract it, we find the deviation. How far is it? Once we have that, so this W is basically the width of our image. So we will define it when we are calling this function. And then we will use the equation of PID. Now again, you don't have to go too much into detail of what this does. If you want just to know how it works, you can copy the code. Otherwise, if you want to go into detail, I would highly recommend you check out any of the other videos on YouTube that have plenty of information about PID. So we are going to write here that our speed is equals to PID. This is a constant value. So we are basically changing the sensitivity of our error by this value. So we will declare it here. We will call it PID is equals to, and we will give in the values of our PID. We are going to use 0.4, 0.4 and 0 in our case. So this is proportional P, this is integral, and this is derivative. So we are only going to use P and D, we will not use I. So here this is proportional, this will be P, and then what we will do is we will multiply this with the error, and we will add the PID1, which is your derivative. We will multiply it with the error minus the previous error. So this will give us the speed, and what we will do is we will clip this speed between minus 100 and 100. We don't want it to go above 100, we don't want it to go below 100, minus 100. So we will write here speed is equals to integer, we will convert it into integer, and we will say numpy dot clip, and we will clip the speed between minus 100 and 100. So this is our new speed for our yaw that we can send in to our drone. So if you remember, for the drone we can send in the value something like this. So we can say me dot send underscore rc underscore control, and then we send in all the 4 values. So the first one will be 0, the second one will be forwards and backwards, so it will be this, and the third one will be 0, and the fourth one will be the yaw, which is our speed. So this is how we can send our command to the drone. Now one more thing that we have to do, we have to return this value, return the error, because we need to use the previous error. So this error, when it comes back here, it will come back as the previous error. Okay, so here we are going to write error. Is error global? No, it's not global, but we can write p error as global. So yeah, we can do that, and then when we call it, so let's call this function. So after we detect that, we are going to send all of this, and we will get back the p error, which we will send in the next one. Okay, so here we have to include the code for the drone. We will still wait for that. We are sending in the info, which is good. Then we need to send in the width. So where can we define the width? We can define it up here. We can say that our width and height is equals to, let's say, 360 by 240. As we did earlier as well, we can resize our image based on these values. So we can write here image is equals to cv2 dot resize, and we will give in our image, and then we will say that we want it as width and height. So this will be the value, and then we can send this, and we already have PID at the top declared, so that should be fine. Now again, you can change these values. If you don't find good results, you can change these values and try out different parameters. I did not put much effort on tuning of this because tuning usually takes a long time, so I'm showing you the basic method, and later you can tune it yourself and see how it works. Okay, so that being said, what else is missing? Do we have anything in the track face? So in the track face, one more thing that we have to do is that we need to define that if we do not get anything, then we have to stop. So we have already defined it for this forwards and backwards, but we didn't define it for speed. So just to make sure, we will write here if our, let's say, x is equals to 0, then our speed is equals to 0 and our error is equals to 0. So our previous error will be 0. Okay, so that is good enough, and now we can bring in the code for our, or let's print out, actually let's remove this and let's print out these values. So let's remove this and let's remove this, and we will print out the value of the speed and the forwards and backwards. So we will write here print and error and FP. So let's run this. Okay, so we have an error. So FB is not declared. So let's go back up, and is it changing every time? So we can write here FB is equals to 0. Okay, there you go. So let's look at the webcam, and there you go. So we are getting the center value, and this is let's remove the other prints because it is annoying. Okay, let's try it out again. So as you can see, the first one we are getting, so you can see here we are getting forward, so we are getting backwards because it is too close. And then if we go back, I think it is too big to actually display here because the 6000 value is too small. So we can try it out later, but for the angle we can see that if we move left or right, you can see that the speed changes, and when it's at the center the speed will be close to 0, and then we start moving away, the speed will increase further. So that is the basic idea, but here we are seeing that it is going to negative 180. So let's see why that is happening. So here our speed, oh, because we are displaying the error, we should display the speed and not the error. Okay, so now if when it's 0, it's displaying minus 100. It should display 0. Yeah, because we need to print it down here. So this is right before it goes to our drone, and there you go, the speed is 0. So once it's detected, there you go, and yeah, it works fine. So now we can test it out in the actual environment, but before we do that we need to add the part for our drone. So let's go to image capture and we will copy the code from there. So we will copy all of this, and we also need to copy DJI Tello Pi. So we will paste it here and we will remove the import CV2, and then we will go to image capture again and we will copy these 2 lines of code, or maybe just this one. We can copy it from here, and if we go down we can remove this, we can comment it, and we can paste this one here, and that should give us the frame. And we can comment this and we can uncomment this part that will send the values to the drone. So let's not print out anything, And then let's try it out and see what happens. Now we need to add a safety feature as well. So when we press the Q button, it will land, and we need to add the takeoff part as well. So here we will write me.takeoff. And what I have observed is that when it takes off, it's at a lower level than the average height. So what we can do is we can make it go a little bit higher so that it's easier to detect the faces rather than going down and bending. So we can write here that actually let's copy it from down. Where is that? There you go. So we can copy it from here and we can paste it here, and we can say that we will not go in the forward, backwards, or yaw. Instead we want to go up and down. So we will go up at the speed of 25, and we will do it for, let's say, time.sleep. We will do it for 2.2 seconds. So it depends. If it goes a little bit higher, then you can reduce it. If it's lower, you can increase it. And then for the landing, we can write something here. Now this will be a little bit confusing, but just understand that this part of the code, when we press the Q button, it will stop, it will land. So we are using the CV2 library to actually do this. So we will write here if CV2 wait key 1 and 0xff equals ORD, we will write Q. So if the Q key is pressed, me.land, and then we will break. Break means we will finish the while loop, so it will end. So that is the idea, and that should work. So let's try it out. If you like the video so far, give it a thumbs up and don't forget to subscribe. In this project, we are going to create a line following drone. Now, the idea behind line following drone comes from the line follower robot. So let's try to understand how that works, and then we can implement the same methodology on our drone. So let's say that we have a line following drone which looks something like this. If we Google the results, you will see something like this. So you can see we have a lot of different types. Most of them, they have a long chassis, and then at the end they have sensors. So it can be 3, it can be 16, it can be 8. So a lot of different types you can see here. So this is, let's say, the exact same robot. It has these 2 wheels, and we are looking from the top. And these are the 3 sensors that can be either on or off. So if, let's say, the robot is on the black line, then it will be on. If it's not on the black line, then it will be off. So at this point, these 2 will be off and this one will be on. So let's have a look at the concept. So let's say I want to move forward. Now here, this middle one will be on and the left and the right one will be off. So the robot will move forward. Now, once it reaches this point, now both the right and the middle one are on, because the black line is both available on the right and on the middle sensor. So then we can tell it to rotate a little bit. Now if it keeps going further and it comes to a point where only this one is left, it means that it needs even more rotation. So, and in that case, we will rotate even further to come back to the middle part until we get this point. Then it will keep moving forward, and at some point you will see that maybe this one and the center one start detecting the black line. Then at that point you have to go backwards in the anti-clockwise direction. So this way, if we have this sensor on, we need to rotate in the anti-clockwise. If we have this one, we need to move clockwise. So we are always moving towards the center of our line. Now if we talk about binaries, if we talk about numbers, if there is no sensor with the line available, then we can say it is 0, 0, 0. Now if one of them is on, then we can write it as 0, 1, 0. So we can have all these different conditions where we can say if it's 0, 1, 0, then go forward. Then let's say that we have this. In that case it will be 0, 0, 1. So if we have 0, 0, 1, we can go right. So we will rotate towards right. And if we have, let's say 1, 0, 0, which will be this case, then we can say go left. Okay, so this one is straightforward, but because we have 3 different sensors, the possibilities are 2 to the power of 3, which means 8. So we have a total of 8 different possibilities. So we have written down 3 of them already. So here we can say it is 2 to the power of 3, which is equals to 8. So we have written 3. Then we can also have 0, 1 and 1. So we will say slight right instead of going right when it is like this. So when it's in the middle, it will have 0, 1 and 1. So this way both of them are on. So we only have to rotate a little bit. Earlier it was 0, 0, 1. We had to rotate a lot. Now it is 0, 1, 1. So we have to rotate a little bit. So that is slight right. So the same way we will have 1, 1 and 0. So this will be slight left. And then we will have 0, 0 and 0. And then we will have 1, 1 and 1. So a lot of the times maybe one of them is not possible. Like for example 1, 1, 1, maybe it's not possible. And 0, 0, 0, maybe it's not possible if it doesn't go out. But at some cases they can be possible. So we can write, for example, stop and stop for these cases. So we have now 1, 2, 3, 4, 5, 6, 7 cases. And the last one is 1, 0 and 1. So again, this should not be possible. So we will write stop, or we don't need to define it. So here we have 8 different possibilities that can happen. So based on this, we can move our robot to follow this line. So it will rotate, then it will go forward, it will rotate a little bit, and then it will keep going forward. So this is the main idea. So let's see how we can implement this to the drone. So here we have the rotation of the drone. So let's say that our drone is up here and it is moving forward and the camera is facing downwards. So we are looking directly downwards. Now we are going to use a clip to actually attach a mirror so that it can look downwards. This clip is available on Thingiverse. Now if you cannot print it, or you don't have a 3D printer, you can always glue a mirror on the Tello Drone itself. I have tried it with the glue gun and it works perfectly fine. But a neater way, a cleaner way, is to use the Thingiverse file. And this file here is provided by Works of Clay. So thanks to the guy who actually built this, and you can see it can view from the top. If you add a mirror, there you go. I think this is the guy. And yeah, so you can print this. It will print quite quickly, and then you can use this to view downwards. So this is what we are doing. We are viewing downwards, and what we will get is we will get an image. So what we will do is we will split this image into 3 different parts. So we will have left, center, and right. So this will be exactly the same method of our line follower. So like this line follower had these 3 sensors, the same way we will have 3 regions where we will detect our black line. So when we are getting the image, if the image is in the middle, then we will say that go forward. Then if it's on the right, then we will say rotate towards the right. So the drone will rotate towards the right, and then it will come back to this position, and then when it goes a little bit here, then it will move towards left and it will travel like this. So this way it will follow the line completely. So the idea is exactly the same as the line follower robot. All we are doing is we are converting our image to 3 different sensor zones. So right, middle, and left. Now because these are virtual zones, what we can do is we can split them into more regions as well. We can make them 5, we can make them 10. But the problem is, if we have more than 3, let's say we have 5, then we will have 2 to the power of 5 different combinations. So that is a lot of combinations to handle. So I would suggest to go with 3. And if you want to try it out, you can try with 5 as well. Now this is part of rotation. Now because in a line follower robot we can only rotate, so it is a bit easier, and that should be enough for the line following. But in a drone, apart from rotation, we can also translate. So maybe the drone is not here, maybe it's here. Then it's not actually viewing the line properly. Maybe it's like this, or maybe it's like this. So we have to make sure that the drone is always at the center. And then when it's at the center, then it will be able to tell when to rotate properly. Otherwise, if it's here, it will not be able to tell how to rotate or how much to rotate. So we also have the problem of translation. So this is the idea of translation, that when the drone is moving, at any given point, we will try to find the center of our black line and where the drone is. So if the image or the line detected is right in the center, we will keep going forward. If it's not, if it's deviated, we will add some translation back towards the center. So the same thing, if it's going this way, let's say it is like this, then we will reduce it back to this. So at any given point, we will measure, so it will keep coming back like this. So this is the idea of translation. So let's get started with the implementation. So the first thing we will do is to right click and go to Python file, and we will create the line follower. So we will open that up, and here we are mostly going to use the OpenCV part. So we will be doing image processing a lot of the times. So what I will do is I will use my webcam, and once everything is done, we can implement it on the drone. So the idea here is that we are going to lay down the A4 papers as our path, because it is very simple to find A4 papers and everyone has them. So this will be a very easy way to create a path. So we will be using A4 paper, but you can use anything that you want. One good thing about the A4 paper is that it is plain white, so we can use color detection to actually detect our white color. So let's get started with that. So what we will do is we will write down here import cv2, then we will add our webcam. So we will write cap is equals to cv2 dot video capture, and we will put it as 1. You can put it as 0 if you have only one webcam. I have multiple, so I'm using 1. Then we will write while true, and then we are going to write underscore image is equals to cap dot read, and that should give us our image from our webcam. And then we are going to write here cv2 dot wait key 1, and we also need to show. So we will write cv2 dot im show, and we will say output and then image. So this should give us our image, and also we can resize it so that it is not too big. So we can write here image is equals to cv2 dot resize, and we will give in our image, and then we will resize it to, let's say, 480 by 360. Again, you can use other values as well if you wish. Now the thing is, when we will be using the Tello drone, the image will be flipped vertically because we are using a mirror to actually find the image, so it will be flipped. So we need to flip it back. So we can write here image is equals to cv2 dot flip, and we want to flip our image in the vertical direction. So that's how you can do it. But for now we are going to remove this, and later on when we are implementing it to the drone, then we will add this again. Okay, so by the way, for now I have these images. So I have created these simple images. We are going to test on that. So this represents the path, the A4 paper, and we have a straight and we have a curve. So we can use the webcam and these images to actually try them out. I will put these images on my website as well, so you can download it from there. By the way, everything will be available on my website for free. You can download the code and all the resources from there. So the next step would be to find our path. So to do that, we are going to use the color method. We will create a thresholding function, thresholding, and we will give it an image that we want to find the color from. So we will copy this and we will write here thresholding, and we are going to use the HSV color space to find our color. Now, if you're not familiar with this, again, you can go back to my OpenCV course and you can check that out. I highly recommend you do that. But if you don't want to do that, then just keep along and I will explain as much as I can. So we are going to convert it into HSV. So this will be our HSV image. So we will write here cv2.cvt color, and we will write that we want to change this image to HSV. The reason we are converting it into HSV, which is hue saturation value, is because it's easier to find colors in that color space. So we are converting from RGB to HSV. Actually BGR to HSV, because OpenCV uses BGR. So we will write here cv2.bgr, color to BGR, BGR to HSV. So this is what we will use, and then we will give in our limits. So we have the hue minimum and hue maximum, then we have the saturation minimum and saturation maximum, and the value minimum and the value maximum. So we have to input these values. But how can we get these values? Well, I have written down a script. Again, this is from my OpenCV course. So this script basically helps us find these 6 values. So let me create a new file here. Color picker. We will create a new file and we will paste it. So this is the code. Again, this will be available on my websites. So what we can do is we can read it from our capture device. So we can uncomment this and we will comment this. So again, this color picker you can use with the drone as well. I have added the code for the drone as well. So when you want to tune for the code for the drone, then you will use this as well. So right now we are using it for the images. So let's run this. So there we go. So here you can see, oh, I think it's flipped. Let me remove the flip. So here, because of the drone flip, I have added the flip here as well. So it is a little bit confusing. So we can run it without that. And there you go. So now you can see my screen, there's black and white. So we need to find this white. So what we have to do is we have to move these values and we have to keep the white color and we have to remove. You can look over here. You have to keep the white color and you have to remove the black. There you go. Now it's removing and there you go. Now we are getting only the white. So you can see here the white that was here is now gone. Then we can increase this. It's getting better and we can play with this as well, and there you go. So these are the values that we got. What we will do is we will stop this and then we are going to go and copy our color from here. So we will copy all of this and we will go back to our line follower, and here we are going to declare a new variable and we are going to call this the HSV values. So here we will call it HSV values, or let's say vals is equals to this. So now we can use these values to actually create the minimum and the maximum. So here we will call this the lower whites, or let's just call it lower, and then we will say numpy.array. So here we have to import numpy as np. So we will say np.array and then we will add our HSV values. Then we have upper is equals to numpy.array, and then again we have to add our HSV values. So we can write here HSV values at 0, then HSV values at 1, and then we have HSV values at 2. So the same thing we will copy from here and we will paste here, and these values are basically 3, 4 and 5. So now if we want to create that image, the mask image, so we can write here mask is equals to cv2.inRange, and we will write HSV, and we want to use the lower and the upper. So this will be the image that will only contain the path, the white path that we have, and nothing else. So we can return this, return mask, return mask, and then we can go back here and we can get this mask. Mask is equals to this. So what we can do now is, actually let's call it image threshold. So what we can do is we can display this image threshold. So we can say path. So let's run this. So there you go. So now only the white part is showing, as you can see. And if we go to the curved one, you can see even the curved one, the only part showing is the curved one. so it's detecting only the white portions. So here you can see it's detecting the white portions. Now for the white paper, for A4 paper, it will be a little bit different, so you might have to tune it again. Actually, let me put down a paper and show you what it looks like. So here you can see that this is the white paper, the A4 paper. Now again, as I've mentioned before, once we are done with the code, we will tune it on the drone, from the camera of the drone, so that it will have a little bit of different colors. So we will tune it then. But for now it looks good, but as you can see, my carpet is gray and it's detecting that a little bit as well. So once we tune it, it should be fine. Okay, so now that we have the image of our path, we still don't know where the center is or how much curve is present. So to do that, we need to convert this into a box, and from that box, we will get the center point. So we will create a bounding box around this path, and we will get the center point of it, and based on that center point, we can translate. So if it's towards the right, we will go back towards the center. Again, if it's towards the left, we will go back towards the center. So we will try to keep it at the center. So to do this, we will create a new function and we will call it get contours, and we will send in our image threshold, and we will also send in our actual image on which we want to draw the bounding box. So let's create this function get contours, and we will have image threshold, and we will have image. Okay, so the first thing we will do, we will get the contours. So we will use the function cv2.findContours. Now contours are basically edges. So we are finding the edges in our image, and based on those edges, we will find the path or the bounding box. So here we will write that we want to find it on our image. Again, if you want to go into the detail of how this works, you can check out my OpenCV course. cv2 dot, we are going to use the external method that will give us the outer region, and cv2 dot chain approximation. Again, you can use simple or none. Let's use none. And what this will return is, it will return contours, and it will return us an hierarchy. Now we are not interested in the hierarchy, but because it's going to return us, we are just going to unpack it over here. Okay, so then we have to find the biggest contour from this, because that will be our path. We are assuming that the biggest contour or the biggest region you find will be our path. So here we will say biggest is equals to, by the way, these contours are basically the dots or the points. Actually, let me draw the contours so that you can see what this is. Let's remove this. So let me draw. So cv2 dot draw contours, and we will give in our image we want to draw on that, and then we will draw all the contours, and this one -1 means you have to draw all of them, and if it's just 1 or 2, it will draw the first one or the second one, and so on. Then you have to define the color, so let's put it as purple, and let's define the thickness as 7. So let's run this and see what happens. We are getting an error. Let's see what that is. CV2 find contours, something is missing, I think. Oh, okay. Here it should not be image, it should be image threshold. So we need to find it from the image threshold that we just got the path from here. Let's run it again. And there you go. So now you can see that the contour, you are getting the contour like this. Now the problem is that my computer is showing the white regions on the edges as well, so that is a little bit problematic. Otherwise, if I zoom in, you can see it's getting the edges. Or let me try the other one. There you go. So now you can see it's detecting the path in the correct way. So if I go here or here, if I go back, it will get the bigger one as well, because I have white regions elsewhere. But if it's zoomed in, it should be fine. So while we are using it with the drone, it should be, the background should be different color, so it will be easily detectable. So now that we have these contours, we need to get the biggest one. So as you saw, we can get the biggest one by writing biggest is equals to max of contours. And what is the key that we want to use? The key will be area. So we will write cv2 dot contour area. So this will give us the biggest contour, the points, and then we will convert all of these points, because it will have lots of points. We don't want that. What we want is the bounding box, the x, y, and the width and height. So we will change all of these points into just a bounding box or a rectangle. So we will say that x, y, then width and height is equals to cv2 dot bounding rect, and we want to change the biggest one. So this will give us the x, y, width and height. So we can use the rectangle method to draw that, and we can also find the center of this. So the center, x will be x plus width divided by 2, and the center y will be y plus h divided by 2. So these will be our points, and as we did earlier, we can draw these points. cv2 dot circle. We will draw it on our image. We want the center to be cx and cy. We want the radius to be, let's say, 10. Then we want the color to be, let's say, green. And then we want the thickness to be cv2 dot filled. So that should work. What else? And we can change this. Instead of drawing all of them, we can only draw the biggest one. So there you go. So now we are getting the center as well. So if we zoom in properly, then you can see the center is here. So if we are getting something like this, we will say that our main center is here somewhere, the center of the image. So we have to go back until it's in the center. So it will be like this. So the drone will move like this. So using this, let's check the other one. There you go. You can see we are getting the center. So using this method, we can find the deviation, and from that deviation we can tell the robot to go left or right. So do we want to draw this? Yeah, why not? Let's keep it there. You can also draw the rectangle using these points. cv2 dot rectangle, you can use that to draw that. So all we need from this function is the cx. So we will return cx, and we will go back here and we will get the cx value over here. So now we have done the first part, which is basically for translation. So I can write here, this is for translation. Okay, now we need something for rotation. So as we discussed the 3 sensor method, we are going to use that. So we will call this as get sensor output. Okay, we will create a function called get sensor output. We will send in our image and we will send in the number of sensors we want to use. So the image will be the same, image threshold, and the number of sensors will be 3. So now you can change those as well, but for now we are going to keep it at 3. So let's copy this and we will create a new function here. So now the idea is that we want to split our image into 3 different portions. So if we have 3 sensors, we want to split it into 3 different sections. So we can use the NumPy library because these are matrices. We can use the NumPy library to actually split it. So there is a very good function for that. Let's say our images are called images is equals to numpy dot horizontal split because we want to split it horizontally. We will give in our image, which is the image threshold, and then we are going to give in how many numbers do we want. So we want sensors, which is 3. We want to split it 3 ways. Now one thing you have to make sure that when you are splitting, the size of the image here, the width of the image should be divisible by 3. If it's not divisible by 3, it will not be able to split it into equal portions. So you have to make sure of that. So 480 is divisible, so it should not be a problem. So what we can do is to actually check if it's working, we can print out cv2.imshow and we can write, let's say, we can create a for loop here for image, or let's say I am in images. We want to show the image and we have to give a unique name. So we can enumerate it, and we can get the value of x. So here for the name, we can put the value of x. We can convert it into a string and we can write here IM. So every time it will loop, it will create a new image. So we will have 3 images to show. So let's run this and see what happens. There you go. So now you can see, so this is our main image, and then we are getting these 3 images converted. So let's say that, let me change this screen. Let's say that it is in the center, or let's say it's on the right, it's on the left a little bit. So then the right one will be 0, the left one will be 1, the middle one will be, sorry, this is left one and this is the middle one. So it will be like this. So right now our sensor value is 1, 1, 0. So right now here we have a lot of values. If we had very little values, maybe something like this, then we can neglect it. We can say if it's more than 20%, then we will count it as 1. And if we have it like this, then it's 1, 1, 1. So it will go forward. If we have it like this, it will be 0, 1, 0, sorry, 0, 1, 1, and so on. So this way, now we can check each of these images. So we need to count how many pixels here are white, and based on that, we can say whether it's on or off. So to do the counting, we are going to write here pixel count is equals to cv2 dot count non-zero from our image. And then we can write here that if our pixel count is greater than the threshold value multiplied by total pixels. Total pixels. So what is this threshold value? Well, we can define it up here. Let's say this is 20%. So if it's more than 20% of the total pixels, then it means it is 1. So we can multiply it here. And wait, what happened here? What is total pixels? So total pixels is basically so this will be image dot shape. We have to take the width. So the width is element number 1 divided by the sensors. So for example, our width was 480. It will divide it by 3 sensors. So it will divide it by 3, and then it will give us the width of our single image. So the one that we have split. And then we will multiply it with the image dot shape at 0. So this is the height. So we are multiplying the width by height, and that will give us the total number of pixels. But because we are splitting it up into 3 pieces, we are dividing the width by 3 first. So this will give us the total pixels, and then we can check if the total pixel count multiplied by threshold is less than the pixel count, then it means it is 1. So we will say that send out. So this will be our let's say sensor values dot append. We are going to append 1. So we can declare it here, our sensor out. So these will be the values. So if the sensor is 110, it will have the value 110. So based on every sensor, is it on or off? So here will be else. We will say send out dot append at 0. So this is the idea, and we can show this for now, but later on we can remove this. So let me print this out and show you how it looks like. So print, let's say our sensor out, and we can return our sensor out, and we can unpack it here like this. Okay, so let's run this and see if it works fine. What are the values that we get? There you go. So this one is the middle one, yeah. This one is the first one, and this one is the third one. So let me show you how it will work. So here, okay, what happened? So I think it was unable to find the biggest contour. That's why it gave an error. So we can fix that later on. We can say do all the calculation if something has been found. Otherwise, don't do the calculations. So here you can see that at this point it should be 0, 1, 1. So this is 0, this is 1, this is 1. And then if I go here, it is 1, 1, 0. If I zoom in or if I zoom out, then the middle one, so the middle one right now is 1, the rest of them are 0, 0. So I think this is clear enough. So here you can see 1, 1, 0, then 1, 1, 1, and then 0, 1, 1. So if 20% of the pixels are present, it will consider that as 1. So we do not need to display this. All we need is the sensor values of zeros and ones. So once we have that, the last thing we can do is we can send out all these values to our drone. So how can we do that? Let's have a look. So we will create a new function and we will call it send commands, and we will say that we are going to give in the sensor out, and we are also going to give the CX. So these are the two values. This one is for translation, we got the CX, and this one is for rotation, so we get the sensor out. So based on these values we can rotate or translate our drone. So here we are going to write that our function is send commands, and the first thing we will do here is we are going to do the translation. So let's look at translation first. Translation. So the translation is actually very simple. So we will get the value of left and right. We will call it LR. So this is the left and right value. So this will be basically our CX minus the width divided by 2. So the width is not declared, so we need to declare the width. So we can write here width and height is equals to 480 and 360. So we can write that here as well, width and the height. Okay, so width divided by 2, and we can introduce sensitivity elements. So we don't want to send in the exact difference, we can divide it by something to make the sensitivity a little bit diluted. So this value will control the sensitivity. So I can write here sensitivity, and we can copy it here. So if the sensitivity, the number is high, if number is high, less sensitive. Okay, so that is the idea. And then we can send this value to our drone. So how can we do that? Now we need to make sure of one thing, which is basically that we don't want to give it a lot of value. So we don't want it to give a very high speed. So maybe the speed is coming to 200, or maybe it's coming to 50 or 70. So that is a very high value and it will be very fast. So we need to restrict our translation to a certain value. So we can use the numpy function here again. So we can say that our LR is equals to integer numpy.clip, and we will clip our LR from -10 to 10. So we don't want to go above that. And the last thing we want to do is we want to add a value where the translation will be 0, because at any given time there will be some value of deviation. But what we want to do is we want to give it some room for error so that it's not always moving. So we can write it that if our LR is less than 2 and our LR is greater than -2, which means it's between -2 and 2, then our LR is equals to 0. So at that point it is not going to do anything. So you can write it here and you can combine all of this. And now we can simply send it by saying me.send underscore rc underscore control, and we can send in our left right, and the rest we can keep it at 0 for now. And we can comment this. Now the second part is your rotation. So as we discussed in the rotation, we will have these sensor values. So whether the sensor is on or off, we have to check. So we will say that if our sensor out is equals to 1, 0 and 0, then we will have a curve. The curve value is equals to, let's say, 30. So the idea here is that if the value is 100, then it should turn more. If it's 110, it should turn less. So we can call them as weights. So our weights are basically, let's say, minus 25, then minus 15, then 0, then 15, and then 25. So the idea here is that if we have 0, 1, 0, which is the center, then this is the weight. So you don't have any curve, zero curve. Then if the value is 1, 1, 0, then the curve will be minus 15. If the curve is 1, 0, 0, then the value will be minus 25. On the other side, if it's 0, 1, 1, then it will be 15. And if it's 0, 0, 1, it will be 25. So we can take the weights from here. So we can go down, where is it? Here, and instead of 30, we can write weights. And this is the very harsh on the left. So this will be the first one. So it will be 0. So now we can copy this and we can write the other statements. So here we will write else if the send out, let's put it like this, so it's facing the same line, and here it will be 1, 1, 0, and the weight will be 1. Then we can copy this line several times. How many times do we need? Okay, if we need, we will remove. So it will be 1, 1, 1, 0, then it will be 0, 1, 0, then it will be 0, 1, 1, then it will be 0, 0 and 1. Then we can also have 0, 0, 0, and we can also have 1, 1, 1, and we can also have 1, 0, 1. So in the last three cases, we will not do anything to the curve, or we can put it as 0 to not go any further. So it is up to us. So 0, 1, 2, 2 will be 0. So here this value is 0, 1 and 2, so this is 0. So that's why we are using 0 over here. So if it's any of these, it will be 0. And then we have 1, we can change it to 2, 3 and 4. So these are our weights. Do we need to change anything else? Doesn't seem so. So the only thing we have to do, we have to declare the curve. So we will declare it here that the curve is equals to 0, and we can write here global curve. So that should be fine. And the last thing we have to do, again, we have to send it. So here in the forward speed, we will have a constant speed. So we will have forward speed, and for the curve we will write here curve. So this forward speed we can define. So I recommend to keep it at a slow speed. Don't go too fast, but as you keep improving, then you can keep increasing your speed. So that is pretty much it. So let's try it out and see what happens. So what you can do is you can try out one part of it. So you can try out only translation, and then you can try out only rotation, and then if you want to tune it, you can tune it, and then you can open both of them and work them at the same time. So here, if you want to just run the translation, you will remove the curve, you will make it 0, and vice versa, you can make this 0 as well and use only the curve. So the last thing, we have to add all the things for our drone. So we will go to the image capture, and in the image capture we will copy all of this code from the top and we will paste it here. We are repeating import CV2, so we will remove that. And then, did we repeat anything else? Doesn't seem so. And we also need to take off. So let's take it off over here. So me dot take off, and then we have to write over here. So in the image capture we are going to copy it from here, and then we will go back and we will paste it here. So we can remove this and we can put this, and we can remove this as well. So this will be the flipped one so that our image is straight. So that is pretty much it. So let's go ahead and test it out. So this is basically the drone, and then this is the clip or the mirror that we have, and what we can do is we can simply snap it here. So it's a pretty good and light design. Now it is a bit fragile, so just take care not to break it. So this is how you can attach it, and now you can see the camera from right here. So there you go, as you can see the camera, and now it will view down. So let's run it and see how it works. Now the thing is that it might actually view, by the way, I got this from a store, and let me check the size for this. Of this is about 25 by 25 mm. Yeah, so it's 25 by 25. So you can get this or you can cut it yourself. Now the first time I tried this, I took a mirror, I cut it myself with a cutter, and I just glued it over here with an angle. I just turned on the camera, I looked at the angle, I held it while the hot glue was drying, and it worked out fine as well. So you don't have to get this fancy stuff if you don't have a 3D printer, but if you do, then this is much better, as you can remove it and you can add it very easily. So let's run this now and see if we can find the angle correct. So I will remove the takeoff for now so it doesn't fly on me, and let's connect it and see what happens. So there we go. So now we are getting the live feed from our drone. And yeah, as I was mentioning before, you might get this problem. So as you can see on the very edge, you will see there is a black area, and this is because of the mirror. So what you can do is, if you press it hard enough, so you can see this is the mirror showing you. Now if you press it hard enough towards the upper side, then it will stay. But if it doesn't stay, what you can do is you can take a scotch tape and then you can tighten it from there. So something like this, and you can pull it back. You can put it here and you can pull it back and then tape it down here. So now it should not give you any of the edge that you were getting before. So let's try it out. So there you go. So there is no edge now and it is fine. So the first thing we have to do, we have to find the color. So again, we are getting this error for the biggest contour. So what we can do is we can go down, and the problem is where? Max. It cannot find max if it didn't detect anything. So let's go to the max. So here we can write if the length of contours is not equals to 0. So we can write that. Hopefully this will work well. And we can define the cx as 0, so that if it has to, it can return just this. Okay, let's try it out again. Okay, so now what we have to do, we have to first of all find the color. So I will lay down the A4 papers, and then we will find the color of using the drone camera. So let's go to the color picker, and we will run this. Okay, we need to change it to the drone camera instead of this. So we will remove that and let's run it again. So there you go. Okay, again, it's not flipped, so we need to flip it here. Let's run it again. There you go. So now I can move these to find the optimum value for the white. So we want to keep the white area, so remember that. There you go. It's getting nice and good. Can add a little bit of this. There you go, and then maybe a little bit of this. Okay, so these are the values that we have found, and it should be fine. So we can stop it, we can copy it from here, and we can go to the line follower and we can paste it in the HSV over here. And if we run this now, there you go. So now we are getting our path. This is the center of our path, and as you can see, we have a little bit of right and left, and then we have the forward speed. There is no curve, but if we rotate it, we should get some curve. So now you can see that we have a curve. If I go on the other side, you can see the curve value is changing. The last one over here, 15. So if I go back, and I think the battery died. Okay, anyways, the idea is this, that everything is working fine. All we have to do now is to try it out, and we will take off and run it and see what happens.